Thanks a lot for the invitation, and thanks for coming. I'm going to tell you about some joint works with Roland Bauerschmidt, Nick Crawford, and Andrew Swan, this object called the Arboreal gas. And there's a few people here who are really completely up to date, and I'm sorry, enjoy the rerun, but I'm going to make it sort of starting from the beginning because I imagine there's many people who don't know what it is. Okay, so first I'll just write down the definition, and then I'll tell you why it's actually interesting. So I want to look at the following thing. I fix some finite graph, and I'm going to fix finite. And I'm going to fix some temperature parameter, beta. And maybe to make everyone very comfortable, let's make it positive. And then I want to look at the following measure. The probability of seeing some subset f of edges is going to be just some normalizing constant, the partition function, beta raised to the number of edges, and then I'll insert an indicator that the graph with the vertex set v and edge set f is a forest. Okay, so forest means acyclic subgraph, no loop formed. So arboreal gas means it's a gas, and the individual components of the gas are the trees, just like a forest is made of the trees. Okay. Just to be completely sure we agree. That configuration would have weight proportional to beta to the 4. And that configuration is forbidden because it has a cycle. I don't count an individual. It's beta to the number of edges in the forest. Yeah. Not the number of vertices. Yeah. Yeah. OK, good. So it's good I did the example. OK, so why? As Bauman said to me many times, a model for what? So we always say it's a model, and then we start talking about it, and what are you actually trying to analyze? And actually, the first place this shows up in the literature is in the physics literature, where people were asking about it as a model of gelation. So this is also an interpretation of percolation. You think of vertices are some kind of molecular units. Edges are chemical bonds. And then you ask, you have some polymers that are being formed by bonding these molecular units together. And you ask about if there's a gel. So the trees correspond to what are known as branched polymers, meaning that they can split or ramify, but they can't have any closed loops in them. And then if this is your perspective, the question you want to know is, are these polymers tightly wound together to form some sort of macroscopic object or not? And that would be the gelation transition. So right. So in some real gels there would be, but in some there would not be. So it depends on the bonding rules of the particular molecular units. So this was Lubensky and Isaacson in the 70s who came up with a model, and they go to some pains to say, oh, by the way, you can actually come up with molecular bonding rules that actually do require no cycles. Actually, their rules allow there to be one cycle per component, but they say that shouldn't matter, let's ignore it. It does matter, but still ignore it. OK, so from this point of view, the question is, as you vary beta, meaning you make it more preferential to form bonds or not, do you see a macroscopic? OK, so just to be. So if you allowed there to be cycles, then you would just be asking this question about percolation, and this would be your interpretation of the percolation transition, that there is a gel being formed. OK, I have to say, this is not our original motivation. Our original motivation will come later. But
it's not obvious that that's the only kind of transition that can happen, right?
You mean the word giant is incredibly vague, or?
No, I mean in the actual
Oh,
right?
sure.
It can be locked together without the...
In an actual gel, I imagine there's things I have never thought of, and like I said, it's not our real motivation. The real motivation will come, but this is a picture to have in your mind why you might wonder, do giant trees emerge or not? Okay, so if this is what motivates you, then one thing you might wonder is there at least an ungelled phase? That should be easy to show, and that is easy to show. And that's because there's a stochastic domination by percolation. So this is P bond percolation. With P being beta over 1 plus beta. So this observation might not be immediate to you. The idea is that you take percolation and condition on the configuration having no cycles. You check that that is indeed this measure for this change of P to beta, and then you're conditioning on a decreasing event. So this gives you the stochastic domination that you want. Okay. So you know that, at least in the setting of a finite graph, there's at least some regime uniformly in beta and uniformly in the graph where all the trees are small. And then the next question is there going to be a regime where there are big trees? You might also want to think about infinite volume instead of finite graphs, but here we already hit a difficulty with this model, which is what's the role of boundary conditions? To take some boxes in ZD increasing to the whole lattice. We don't really understand that question at this point because this model, the arboreal gas doesn't really have nice monotonicity properties. So this is sort of going to be the style of the talk where I tell you something and then I list a question because there's many questions we don't understand, and that's what I'm hoping to mostly tell you about as opposed to details of proofs. And you should interrupt me at any point if something's not clear.
Whether there's some sort of infinite volume goop measure which is more natural than others. Is that what you're asking?
Right. I mean, sort of, it's tempting to think that they're basically all the same on ZD. There's only one.
It's tempting.
But OK. That's as far as I'll go for now. So the plan is to tell you about mostly results and conjectures. And really to motivate this model or its study for the reasons we were initially interested in it, which is by comparison to percolation, which is familiar to many people here, and also to the classical Heisenberg model, which is probably a little bit less familiar to everyone here, although, of course, familiar for many of you. OK, so before I tell you about the arboreal gas, let me remind you of, I don't know, a couple decades of work of percolation theory and one theorem. So I won't attribute it because it's not fair to attribute it to any one person. So this is bond percolation on ZD. If D is at least 2, then there is a gelation transition. And one way that you can summarize basically everything we know is to say the following. Let theta p the probability that 0 is connected to infinity. Then, so I'm telling you things that almost everyone in this room knows, so apologies for that. But there is some critical probability p. So that as long as you're away from criticality, then the probability that 0 is connected to a distant point x is basically theta p squared plus a correction. And the correction is quite small, exponentially small in x. And the point is that this first term is 0 if you're below criticality and positive if you're above criticality. Okay, so it's a familiar theorem, or it contains familiar parts. It says that there's a giant component in percolation, which we actually know is unique, although it doesn't quite follow from this formula. And the giant occupies density about theta. The chance that two distant points are in the giant, it's like an independent trial with an exponentially small correction, which says that if you're not in the giant, you're in a quite small component, actually. So this says, okay. So this is, like I said, the work of, I don't know, 10, 12, 15, 20 people over a couple decades. Let's compare that to what happens for the arboreal gas.
Then the error is positive.
Pardon me?
When you wrote plus something, is it known that it's positive?
Well, I guess I wrote this weird symbol, which I didn't even say what it means. So, but I think it is plus. Yeah. But it really is plus. Okay, so, well, for the arboreal gas, there is a gelation transition. If D is at least 3. Okay, so let me formalize that for you, and this takes a little bit of setup. This was with Nick and Roland. So I'm going to look at a d-dimensional torus of side length n, or L to the n. And for some technical reason, L is going to be some big number. And, OK, D is at least 3. Then, if I take beta large enough, I have the following thing. And I realize this is really the worst place to do this, because I'm going to have to move the theorem over to the other board. OK, well. So if beta is large enough, meaning I'm making the force really quite dense on the torus, then there's some theta of beta, which is close to 1. Some constant c of beta, which is order 1, and some positive kappa, such that the following is true. If I look on the torus and ask in the arboreal gas, is 0 connected to some distant site x, then this is equal to theta of beta squared, and then a correction that's polynomial, and then some terms which are smaller. Which let's think about as being 0 for now. So this says, again, you see a giant component, and if you're distant, it's sort of like independent trials to be inside. But this says that if you're not in the giant, maybe off the giant, you're critical in some sense because you have polynomial decaying correlations away from this giant component. And the other two terms are error terms, which I don't really want to say anything about because they're error terms, so they're not that interesting to talk about.
And this time you wrote equals, right? So that's the error term here is on the notes.
Yes. Yeah. So this is the giant tree. And let me emphasize, this is in finite volume. So this is really just on a fixed torus. So we haven't had to deal with any of the issues of infinite volume limits. But everything is uniform in the size of the torus contained in these errors. So it extends to infinite volume limits if you want to take them. OK, so there is a gelation transition in 3 and higher dimensions. If you want to make jello out of a branched polymer, it works in our world. But in flatland, it doesn't work. So in d equals 2, there's no gelation transition. So this was also with Andrew. And what I mean by that is if you take some finite subgraph in Z2, then on this subgraph, the probability that 0 is connected to x decays polynomially in the distance to x for some c of beta positive. OK, so what this says is that if you look at the, say, the expected size of the tree containing, or that contains the origin, this does not have positive density. So in that sense, it says there's no giant tree. OK, so to what extent this is surprising, I guess, depends on if you had a prior belief about what should happen. On the one hand, it's very different. Yeah, so it's very different than percolation. But of course, we did some horrible conditioning to percolation. So well, in infinite volume, this is incredibly singular, right? So.
Wait, in 2G, this is for any beta, right?
Any beta, yeah. I mean, yeah, for C is a function of beta that we get, but. OK, so I would say we were surprised. I think it is surprising. Again, this is a finite volume result. You can transfer these things to infinite volume in some sense. So let me just remark on that briefly. So
sorry, I missed. What is capital N?
Capital N is my index for the torus. So the torus has side length big L to the capital N, and then I'm taking capital N to infinity. Yeah. In infinite volume, translation invariant limits can be partially understood. What I mean by that is that in 2 dimensions, this theorem can sort of be boosted with a little work to say that there's no infinite tree either. It's not just that it's not a positive density. There's really no infinite tree. The downside is we don't know that all the limits are translation invariant, so this doesn't really completely answer the question. And I should say that a much more robust version of this, compared to what was in our original paper, is due to Tom and Noah Halberstam, who also showed that so they showed that in 3 and 4 dimensions, when there is if there is an infinite tree, there's 1 in 3 and 4 dimensions. But it's open to show there exists infinitely many in D at least 5. Okay, so just to say the words in case someone is not familiar, the idea here is that if you take a really high density arboreal gas, maybe you think it looks sort of like a uniform spanning tree. And then P. Mantel's theorem is that it has infinitely many components in 5 and higher dimensions, but not in 3 and 4. It's also open that there's a unique giant in finite volume. Okay, so it's slightly annoying that we can say that this constant goes to 1. So there's, really, it's filling the system up, but we can't say that there's just one giant and there's not another one hanging out, even in 3 dimensions when we know in the limit only one of them is around. Okay. Any questions about that before I move on to the Heisenberg model, which maybe is a little bit more illuminating to see what's really happening? Okay. So the Heisenberg model, for those of you who haven't heard of it, different than the Heisenberg model mentioned in Dora's talk earlier, although the same Heisenberg. So this is like a version of the Ising model, but instead of plus minus 1 spins, they take values in the 2 sphere. So your spins live in the 2 sphere, and I'll write their components as x, y, and z. And it's like the Ising model, by which I mean that the law of the collection of spins, which I'll call ui, I are the vertices in my graph. Well, there's again some normalization. And then I have sum over all nearest neighbor edges. And then I just look at the inner product of the gradient of the spins along that edge. And I integrate with respect to a uniform measure, product uniform measure. Okay, so everywhere you just have your vector pointing in some direction in 3 space, and this makes them want to point in the same direction. And just like the Ising model, you wonder if they collectively point in the same direction when beta is large to make this favorable enough. So now there's some classic theorems about this model, which has been studied for a long time. And the first one is a rigorous theorem, which is the analog of what Dora was saying about the fact that the interchange model shouldn't have long cycles in 2 dimensions. So this is the Mermin-Wagner theorem. So it says that if d equals 2, there's no long-range order. It's a much more general theorem than being for Heisenberg, but let me write there's no long-range order for Heisenberg, by which I mean if I look at the inner product of the spin at 0 and x and compute that in expectation, this decays polynomially with some positive rate for any beta in 2 dimensions. This is not what Merman and Wagner proved. This is the McBride-Spencer formulation of the theorem, but let's not worry about the detail. The idea is, think about spins pointing in the same direction. Then they're still going to fluctuate a little bit around that chosen direction that's favorable. And that's going to be like a Gaussian fluctuation. And in 2 dimensions, that means that the fluctuations are like the Gaussian free field, and that has infinite variance in 2 dimensions. So they're going to be moving, dramatically far from the direction you said they're pointing in. So it's not consistent to say that they point in the same direction. And that's why there's no way to get them to all point in the same. Order would mean that this is like a constant that doesn't decay. And that argument says that won't happen. And you can make it full. OK. And the counterpart to that is a theorem of Froelich, Simon, and Spencer, who said that in 3 dimensions and higher, and beta is large, then long-range order occurs. There is some C, again, this should depend on beta. So that the spins really do point in the same direction, even as 0 and x become very widely separated. OK, so I guess the comparison is clear. The phenomenology is exactly the same for the arboreal gas and for the Heisenberg model. And it's worth remarking that the correction to this is order x to the minus d minus 2, just like it is for the result I put on the board over there. That's a theorem due to Balaban that's famously pretty hard to understand.
Is it related to the work of Dario and Wu?
So for the rotator, Dario and Wu would have said that they can compute the next order term also and compute the constant in front. But for Heisenberg, I don't think their method currently applies. Yeah, but you're right. I should also say, I think it's fair to say Dario and Wu is also pretty difficult. They have to work hard. OK, so it's not a coincidence at all, of course. What's happening? So what's happening, and the reason you could even predict that these things behave the same, was found by Caracciolo, Jacobson, Sokol, Salur, and Sportiello in, I guess, a very short paper that has then since occupied quite a lot of my life and my co-author's life. So why? They made, I think, at least for me, the remarkable observation that the arboreal gas is really a spin system with continuous symmetry. Okay, so this picture I told you for Heisenberg about why there's no transition in 2 dimensions, that you look at the fluctuations of this continuously moving spin. In some sense, that also applies to the arboreal gas. As I'll tell you in a moment, you have to sort of squint quite hard to make that picture work because the spins are going to be a bit weird. But in their paper, their letter, when they noticed this connection, then they wrote down, that it will behave exactly like the Heisenberg model, because if you do some non-rigorous physics renormalization group computations, all the predictions for Heisenberg you get for the arboreal gas, at least for leading type behavior. So they knew right away, not as a theorem, but as a prediction, that this is what was going to happen. OK, so let me give you some taste of what this means, although I won't give you all details. So I'm going to do it in steps by first saying, if we're thinking about Heisenberg, we're thinking about the two-sphere. So that's x squared plus y squared plus z squared equals 1. Nothing surprising. And here, the symmetries are rotations. To ease my life slightly, let's go from S2 to H2, the hyperbolic plane, which you can think of in the hyperboloid model as being solutions to this equation, where z is non-negative. And you have symmetries again, but in particular, you have things like boosts. So this is the hyperbolic plane. OK. And what CJSSS noticed, although they used different words, they didn't say it this way, but this is the way we like to say it, is that you should do the following thing, right? Instead of putting the 2 on the left of the bar, usually we just ignore the things that comes to the right of the bar, but you can remember that it's there, and write H02. And what this means is that you change x and y, which are parameterizing the hyperbolic plane, from being commuting variables to being anti-commuting variables. OK, if you've never seen that before, you probably don't like it too much. And I'm not sure I'll convince you in the time here, but let's just see what that means. So these equations were coming from taking the appropriate inner product and setting it equal to 1 or minus 1. So this is the Euclidean inner product, and this is the Minkowski inner product. So here, again, we take the appropriate inner product and set it equal to minus 1 to mimic the definition of the hyperbolic plane. So what you get is that is this equation. OK, so this is just an algebraic equation now between, or it's an equation in some algebra involving these anti-commuting variables, psi and eta. And what this means, by definition, is that z is the positive solution to this equation. And you might not like seeing this because I just told you these are anti-commuting algebraic objects. So what's the square root function? It's just defined by power series expansion. So any function is defined by power series expansion. And every expansion terminates in finite order. So this is a consistent way to define functions. So this is just 1 minus psi eta, basically by definition. OK, so then the model, H02 model, is defined by the same formula as the Heisenberg model. up to reinterpretation. So for the Heisenberg model, everywhere I had x, y, z, and now everywhere at every site, and now I have u equals psi eta z, where z is defined by this equation. And okay, integration I don't have anymore, but there is a notion of integration over such an algebra. So integration means you just take out the top degree coefficient of whatever you're integrating. So this is an algebra of anti-commuting variables. So as long as there's only finitely many of them, there's a highest possible order term. And integration just means, well, look at the highest order term and take its coefficient. Okay? If you're not familiar, it's a strange rule, but it's very useful and behaves a lot like integration, so it's a good definition. But, you know, as I think is clear, it's not probabilistic, which of course doesn't mean it's not useful. So if you unwind all of these definitions, what you find is that the probability in the arboreal gas that 0 is connected to x, meaning they're in the same tree, is the same as the correlation between psi0 and eta x in this H02 model, which is amazing, I think. Okay. So it's actually very simple to prove that this is true. I don't think I'll give you the whole proof now. Actually, there's even more than one proof. So one proof goes by using the fact that H02 has a certain nice set of symmetries, and by using those symmetry operators, you can learn theorems like this. That's the proof that we liked by having this hyperbolic interpretation. But you can also just prove it using the matrix tree theorem. So
is there some sort of expression for this probability in terms of inverse Laplacian Green's function stuff?
It doesn't quite mean that, and I'll write down basically the reason why it's not quite that good. So basically what they do is say, look at the definition of something like this, or even just look at the definition of the partition function of the H02 model. Unwind all the definitions, get the part that looks like the matrix tree theorem and something else, and expand the rest. And then use the following fact. If you have a tree, the number of vertices is one more than the number of edges. And basically what they show is that every term that contributes to the integral where you see a tree, either it's rooted at a vertex or it's rooted at an edge with a -1. And that linear combination then ends up having no roots for the trees. So this is why in the end you end up with a forest of trees with no roots. But this sign showing up makes it hard to have a simple Green's function formula. Okay, it's not meant to be super understandable. I mean, in the sense that unwinding the definition of this takes some time. But what it ends up leading to is this is the only fact you really need plus the matrix tree theorem. So it's not complicated. Okay. So I think there is a question of how do you actually do this, but let me do that one offline. Are there any other questions at this point, though?
Is there like a coupling between two models, even non-probabilistic?
No, I mean, this is not just non-probabilistic. It doesn't even make sense to say configuration. So what a coupling would mean, I really don't know. This is just if you want some linear functional on the algebra. And for many, but not all quantities, you can write arboreal gas observable quantities in terms of certain expectations in this model. Okay. So I have 10 minutes. Is that right? Okay. So let me tell you some open questions, and if I go fast, I'll tell you some proof idea, but I probably won't go that fast. Okay, one, this is the most important one, and one of the reasons I wanted to talk about this here is because some of these questions have been about what happens in high dimensions, like show there's infinitely many trees in 5 and higher dimensions, but I have to be honest, the most important open question is about 2 dimensions. And it's the following. It's not the truth that there's polynomial decay of connections. It should be exponential.
Does your proof of the power law decay uses the connection to the continuous symmetry spaces?
Yes. So if I have time, I'll get back to it. And if I don't, remind me. OK, so this is for the Heisenberg model. This is sometimes called Polyakov's conjecture for what happens. But because this, pardon me?
We knew that already for beta small.
For beta small, but this is for any beta.
For any beta.
Yeah. Yeah, sorry. I should have written it. So for any beta, there's always exponential decay. So we proved that there's polynomial decay, but that's very far from the truth. And so this conjecture for the Heisenberg model was made by Polyakov a long time ago, and he sort of said this is a simple version of the Yang-Mills problem. It's still pretty hard. This still seems pretty hard, but it should be easier than the Heisenberg question. So let me just tell you a fact, because we saw some very interesting things earlier, yesterday, that maybe tell you why you might think this is plausible. So the arboreal gas is actually the Q to 0 limit of the Q random cluster model if you set P to be equal to beta times Q. And, well, we actually basically know what the critical point is in 2 dimensions for the Q random cluster model. So we know at least when Q is at least 1, that the critical point is root Q over 1 plus root Q. So if this is true, just for Q positive, then the critical point blows up as you go to Q equals 0. So this is what you want to see the critical beta. Okay. Okay, so that's a big if, and you have to certainly show something slightly more. The sense in which you can show this is true will be relevant for trying to transfer it over. But this is one possible approach to showing that you have exponential decay.
Do you also see the relation on the level of the correlation? Like the predicted C of beta as beta goes to infinity versus the exponential decay rate for Durham?
I don't know. I don't know the answer to that. So there are predictions, of course, for how this should behave. I'm not sure if there are predictions for how the correlation length of the Q less than 1 random cluster model behaves as you go to the critical point. I don't know. Unfortunately, we don't really know much at all in Q between 0 and 1. So, OK, so this is a great question. It would be really interesting to know that it's true. Another question is to come back to this question of, are you critical off the giant? So there's there's two contexts where we really know that this is a theorem. So one is Uchak and Patel, who looked at the complete graph, the arboreal gas on the complete graph. And the first thing they showed is that when you look at the right scaling, which is, the beta should be alpha over n. And if you ask how big is the tree containing some fixed vertex, well then it's order 1 if alpha is less than 1. It's of order n if alpha is bigger than 1, just like for the Erdős-Renyi random graph. And the answer in the middle is also the same. Expectation is order n to the 1/3 in the middle. So this is not super exciting. It just says the condition to have no cycles doesn't really do that much on the complete graph. But they showed something that's very interesting, which is that, so if you look in the supercritical regime, alpha is positive, then the second, third, fourth, and so on, biggest trees have size n to the 2/3, just like at criticality. No, because I'm taking the expected size. Yeah. I wrote 2/3 in my notes and then remembered. OK, so in the complete graph, this criticality off the giant can be proven in quite a strong sense. You can even relate the distribution of the second, third, fourth, and so on to the distribution of a certain point in the critical window of the arboreal gas. And the complete joint statistics of this were worked out by Martin and Yao. OK, it's also known that this phenomena happens on the wired tree. So that's due separately to Phil Iso, Gaurav Rai, and Ben Shao. Let me just say briefly, also happens on wired trees. But what about on ZD when D is at least 3? So the prediction is that this will be true if D is at least 7, but not if D is 3, 4, 5, 6. And this is because somehow there's there's numerical evidence that people have worked hard to compute that the upper critical dimension is the same as for percolation for the arboreal gas. And it would be interesting to see even the relevance of the triangle diagram for the model if you know what that is. OK, but what's happening in these intermediate dimensions is, well, this is already quite hard. We don't know how to do it. It would be very interesting to see something. I think I'm out of time, so I'll stop at this point. Thanks.